In this video, I'm going to talk about how we calculate moles when it comes to solutions, and that involves something called molarity. So let's start by talking about solutions in general. Solutions are homogeneous mixtures where you have a solute that is dissolved by a solvent. Because they're homogeneous, they will look like pure substances. You will not be able to look at them and say, oh, this is a mixture. When I talk about a solute being dissolved by a solvent, we're really saying that the attractive forces between the atoms in the solute and the solvent are the stronger ones. They are stronger than the attractive forces that are within the solute itself that would normally hold it together. So to look at this illustration, we have an example of sodium chloride, and in its crystalline structure, we have attractive forces between the positive and negative ions, and that's what's holding things together. They are pulling towards each other. That's forming that crystal. But when that solid solute crystal is put into water, the water molecules are so strong in their attractive force, they are going to pull these ions away from each other and toward the water molecules and cause the solute to dissociate, to dissolve or disappear practically into the solvent. We use a lot of solutions in chemistry. Most of ours are aqueous solutions in the high school chemistry lab where we have water as our solvent and a variety of solid compounds as our solutes. So when we talk about how much solute is in a solvent, in a solution, we're talking about concentration. If a solution is concentrated, it has a lot of solute in there, and if it's diluted, it has a little. But these words just give us a general idea about how much solute is in a solution. It's really not specific enough to do anything with so far as predicting how many products you will get or how many reactants are present. You often can tell if a solution is diluted or concentrated if it has a color by the intensity of that color. So our dilute solution over here you see is a very pale color, and the concentrated one is the very dark color. There are several ways that we measure concentration. One is a percent mass measurement, where in any kind of percent, you've got some piece of the whole, part of a whole thing, and we want to know how much is that part out of the whole. And so you're comparing the mass of the solute in this case as compared to the total mass of your solution. And then if you multiply it by 100%, it turns it into a percentage instead of just a decimal. We use percent mass when we're talking about elements in compounds. In fact, one of the ways to determine the formula of an unknown compound is to decompose it into its various elements, take all those individual masses, and then compare the mass of the pieces to the total mass to give us the percent. We also use percent mass when we have components of mixtures, especially when it's a solid dissolved in a liquid, and vinegar is the perfect example of that. If you look on a bottle of vinegar, it'll tell you it's a 5% acetic acid solution, and that is 5% by mass. So there are 5 grams of acetic acid in every 100 grams of vinegar. If you want 5 grams of vinegar for a particular chemical reaction, you would measure out 100 grams of vinegar, and you know that that's how much acetic acid is present. We also have percent volume, which uses the same principles, but it is used for components of liquid mixtures where you have a liquid dissolved in a liquid. You may be thinking that solutions are always solids dissolved in liquids, but that is not true. There's actually a variety of combinations that will make a solution, though most of the ones we work with in class will be solids dissolved in liquids. So a percent volume would be the volume of whatever part of that, the component, divided by the total volume. Hydrogen peroxide that you pick up at the drugstore is 3% by volume. And so that means there are 3 milliliters of hydrogen peroxide, H2O2, in 100 milliliters of the liquid in the bottle. Very small amounts of solutes may be measured as parts per million or parts per billion. One piece, whatever size you want to make that per, if you had a million of those pieces, so say 1 cup in a million cups or 1 milliliter in a million milliliters. This is something you see frequently when we're talking about toxins in drinking water. So arsenic levels in drinking water are too high if they are above 10 parts per billion. So it doesn't take very much arsenic to cause a problem. Now we come to molarity. And molarity is based on moles. Remember that moles are how we count atoms. It gives us an idea of how many atoms are present. And so molarity tells you how many particles are available to react in a solution. And of course, we are wanting to do chemical reactions because we're wanting to produce products. That's the practical side of chemistry. So to calculate molarity, you take your moles of your solute and divide it by your liters of solution. Per, remember, is just another word that means divided by. If you know any two values out of this, if you know the molarity and the moles, you can figure out how many liters you need. If you know the molarity and the liters, you figure out how many moles of solute are in there. So every time you know two values, you can figure out the third. So we have two examples down here. They both have the same number of moles in it. We'll just say those 13 little yellow dots equal 1 mole. So the molarity of this larger beaker would be 1 mole, and we'll say that it is 1 liter. So it has a molarity of 1. 1 molar is what we usually say, and the symbol is this capital M. Our smaller beaker only contains 400 milliliters, so it is not a full liter. And in order to use the molarity formula, you do have to convert. And if you remember that there are 1,000 milliliters in 1 liter, so if we just take our decimal point from the far right here and move it 3 spaces to the left, you convert your milliliters into liters. So here we'll have our 1 mole over our 0.400 liters, having converted those milliliters to liters. And that, if we do the math on that, is going to equal 2.5 molar. So same amount of moles in much less volume gives you a higher molarity. So let's do some molarity calculations so that you can get familiar with this, and then you will have a chance to do them on your own. This first problem asks, what is the molarity of a solution containing 0.44 moles of cobalt chloride in 654 milliliters of water? So again, your molarity formula tells you you want to have your moles over your liters. We don't know our molarity, so that's our X. Our moles are 0.444, and the liters, again, we have to convert our milliliters to liters by moving that decimal point 3 places to the left. So it's 0.654 liters. So we have our setup. All we have to do is do the math on these numbers. The moles over liters will cancel out because that's how we define molarity. And we find out that the molarity of the solution is 0.679 molar. Simple plug and play, pretty straightforward. However, you know we can't measure moles directly in chemistry. We can only measure grams. And so most problems involving molarity are going to involve some stoichiometry and mole-gram conversions. So here's our first example. This problem asks how many grams of potassium carbonate are needed to make 200 milliliters of a 2.5 molar solution. So let's start by putting together the molarity formula. We know we have a we want to make a 2.5 molar solution. That's going to equal some number of moles over our volume, which is 0.200 liters. Again, we've got to convert these milliliters to liters. So if we go ahead and solve for x, in this case we're going to have to multiply both sides by 0.200 in order to cancel out our liters. If we multiply this side by 0.2, I don't have enough space on the left, but to go ahead and do the math, we're going to end up with x being equal to 0.500 moles. So we know how many moles we have, but now we've got to do a mole-gram conversion because we can't measure out anything in moles directly. We can only measure it out in grams. So we have our moles, and what is our moles? Well, it's moles of potassium carbonate. And so you need to know what's potassium carbonate. Well, carbonate is CO3. It has a -2 charge, so it's going to have 2 potassiums with it. We need to know that so we can figure out our molar mass. And if you go ahead and look up all the values for potassium carbonate, all the individual atomic masses, you know that the molar mass for this is going to be 138 grams per mole. And so we just plug that into our mole-gram conversion, and that's going to give us a value of 69 grams. So we need to measure out 69 grams, or 69.0 grams, of potassium carbonate in order to make our 2.5 molar solution. So in that case, we were asking to calculate the grams, so we were looking at the moles. This problem asks how many liters of a 4-molar solution can be made from 100 grams of lithium bromide. So we're trying to go for 4 molar. We know that we have 100 grams of lithium bromide, so that's going to be our mole value, but we don't know it yet. But we're being asked how many liters, so that's actually our X. So at this point, we're missing both things on the right-hand side, so we can't start with the molarity formula. We've got to start with some mole-gram conversion. So we need to take our 100 grams and we need to change it into moles, and so we need to then calculate our molar mass for lithium bromide. Lithium and bromide are each, lithium has a +1 and bromide has a -1, so it's just a 1-to-1 relationship in the formula. If you go ahead and look up the molar mass for this particular compound using the periodic table, you find that it is 86.8 grams. And so we put that in and this case we're going to divide 100 by 86.8, so that's going to give us a 1.15 moles present in our 100 grams of lithium bromide. We plug in our 1.15 moles over here, and now we can solve for X. We can figure out our liters. Again, in this case, we can cross multiply this to solve this problem, giving us 4x equals 1.15, and then we do the division, we'll find that x is 0.288 liters, or 288 milliliters. So in a very concentrated solution, or a fairly high concentrated solution, 4-molar solution, this 100 grams is not going to go very far. We're only able to make a little over, or not quite 300 milliliters of solution. And then one more example. Again, in this case, we're asking what is the molarity of an aqueous solution that has a volume of 450 milliliters and containing 200 grams of iron 2 chloride. So we don't know our molarity. That's going to be our X. Again, we need to figure out our moles because we're just given grams. And we know that we have 450 milliliters, or 0.450 liters. Once again, we need to do a mole-gram conversion so that we can figure out how many moles we have in these 200 grams. And the 200 grams is of iron 2 chloride, so that tells us that our iron ion has a +2 charge, so that means we're going to have 2 chloride ions attached to it. So off to the periodic table to look up some atomic masses to find out that this is 126 grams. Is your molar mass, and so then 1 mole, if we do the math here for our 200 grams, is going to be 1.50 moles. Now we have our mole value. We can plug that in, 1.50 moles. Go ahead and do the division with the math to tell us that our molarity is going to equal 3.5 molar solution. So those are basically the different combinations of information that you might see the way the problem is arranged to how you set up your formula and then just plug in and do the calculation.